Hi to all, this is my project for the course on nanomanufacturing on wearable devices. Wearable technology is a fascinating research field which can include both an incredible development in the field of material science and of the design area. With ubiquitous computing, wearable technology share the vision of making technology pervasive and interaction frictionless. Here are some examples of everyday life wearable gadget. In the top, we can see Google Glasses, a type of wearable technology with an optical head-mounted display. And in the bottom, you can see Samsung Gear Fit wearable electronic, an advanced curved AMOLED touchscreen display. Here in the right, we can see a LilyPad Arduino, a microcontroller board designed for do-it-yourself wearable and textile project. And here, finally, an example of integrated wearable electronics and fashion with an MP3 player here and the speakers mounted in fashion waist. This is the everyday life wearable gadget, but as many sci-fi fans know, literature, movies, TV serial, comics and video game show us main character using wearable or implanted devices. Let me show you some examples. In the movie Total Recall, the protagonist show an implanted phone, and in TV serial Continuum, the protagonist Kira Cameron, coming from the future with a time machine, can dispose of variety of nanotechnology-based gadgets, as a smart contact lens for augmented reality or a multifunctional battle suit. So this is the sci-fi point of view, but what about the scientific and technological point of view? Because wearable technology tend to be more sophisticated than an handheld technology on the market today. To reach those futuristic goals, we need to explore some new approaches. In particular, the fundamental characteristics are flexibility, transparency, and of course, for biomedical application, biocompatibility. This is a little bit of history, because in the recent year we have assisted and increased in the number of research that focus on the creation of biomedical devices can apply directly on human skin. But flexible electronics has a long history. The development of flexible electronics dates back to the 1916 for the first flexible solar cell array. And in the 1968, we can see the first flexible transistor. But the research on flexible electronics has expanded rapidly in this year, and many research groups and companies have demonstrated flexible display on steel or plastic substrate. And for example, we can see in 25, Philips demonstrated a prototype of rollable electrophoretic display. And in 26, Universal Display Corporation and the Palo Alto Research Center present a prototype of flexible OLED display with full color and full motion. To explore more in depth the potential of this technology, I've chosen to analyze recent really interesting work published in January about transparent and very flexible electronic. Okay, the aims of the project is the development of ultra-flexible electronics. The author will demonstrate the remarkable bendability, conformability, and lightness of the device for biological sensing and wearable or implantable devices. And finally, they can create application to this technology to any object, surface, or biological tissue, such as human skin. Potential application is very a large field with transparent devices, electronic textile, smart contact lens, and electronic skin. Some example of this application are flexible and or elastic substrate as polypropylene, polyamide, and nitride rubber. Application on any arbitrary shape object like classic textile, air bubbles, all simple freestanding. And finally, the biological tissues or implantable device. Here, the device on the plant leaves, on the human skin, or on a plastic contact lens. This technology can be created by the introduction of thin film transistor. That is a technology which is a special kind of field effect transistor made by depositing thin film or active semiconductor layer. Here is a scheme. The common substrate is glass, typically here, because the primary application of this technology is in liquid crystal display. The method of deposition must be completely under relatively low temperature for the nature of this material, and we can see typically chemical vapor deposition or physical vapor deposition, usually with the technique called sputtering. Okay, this is the carrier chip. In this case, the device proposed consists in a ground signal ground layout. Here, this is the scheme of these devices, and here is the 3D model of this source drain gate. And the carrier chip used is a standard 2-inch silicon wafer structure with a standard UV lithography. Okay, this is the circuit typically constructed by an amorphous oxide semiconductor, typically indium gallium zinc oxide, with the sputtering technique at room temperature. An IK dielectric, typically aluminum oxide. The metal is typically gold for the drain and source, but for a specific application like transparent technology, the source, gate, and drain can be replaced with indium tin oxide, always by ambient temperature sputtered. technique that can make transparent technology. At the bottom of this circuit, we can see the membrane. The membrane is a real innovation. In fact, this approach is very versatile and allows different configuration synthesis that can be used for different applications. We can see 4 layers. In the top, the glass or silicon polyamide foil. In the middle, 2 soluble layers. The one is polyvinyl acetate and the second is polyvinyl alcohol. Both are spin coated and baked at 100 degrees, but both are easily and selectively removable for different applications because every layer shows a specific adhesion property. And in particular, polyvinyl acetate is only used in case of transfer onto polyamide foil for rubber, skin or plant leather. Between the circuit and the soluble layer, we can see a non-soluble layer composed by parilene. And parilene is a trade name for a variety of chemical vapor deposited polypolymers used as dielectric barrier. Parilene is also green polymer chemistry because minimizes the use and generation of hazardous substance. And it is chosen because it is biocompatible, elastic, seizable, and show more interesting characteristic for this application. The method of transfer is quite simple. The membrane start dissolving, the PVA membrane start dissolving in water, simple water, and the transfer is from one substrate to another till it dry completely. The membrane is still attached in the center, and when after 13 minutes the wafer sinks and the membrane float on the water because the center membrane are totally removed. The applications are typically in 3 possibilities: the thin film electronics. The author show a schematic of a different amplifier. This is the photograph, this is the schematics. And the device is constituted by 7 transistors, which have a channel length as small as 6 micrometer. This is a flexible polyamide foil, and this is the first application for this work. The second is a transparent circuit, and this is a most interesting sci-fi application because the device in this case is a gold strain gauge sensor transferred on the plastic contact lens. Here this the plastic contact lens. You can see between this finger. Here we can see the circuit transparent, and this is the scheme of the device. Here the membrane transferred on artificial eyes. Here you can see also the circuit on the contact lens. And this sensor can be potentially exploited to monitor the intraocular pressure. And the third and the last application is high flexible electronics. In this study, the authors have to ensure high flexibility and conformity to the circuit, and it wraps around an air which have a radius about 15 micrometer, and the circuit work as well. This application allow to create other devices, can be transferred on irregular surface like plant leaves, for example. So, the final question is, it is realistic to imagine a future when buying sci-fi gadget will be as normal as buying as iPhone? The answer is yes, and the roadmap is traced since 1960s. Of course, before we need to spend more effort in order to investigate material properties and technological application. New perspective will be opened by engineering biomaterial, such as, for example, spider silk is a typical line of research. But finally, we can one of the main questions to be answered is how this pervasive technology will impact our everyday life. Here I collected some useful reference to study more in depth this fascinating field of research. So enjoy, and thanks for your attention. Bye.